That's what I was saying. Okay, so we'll get this party started so that we can go to a faculty meeting, except for you guys. You don't want to go to a faculty meeting, but you can come if you want. Once in a while they have good stuff. It's my great pleasure to introduce Matt. Okay, I've had Matt as an advisee. I'm like losing half of my advisees this year. It's so sad. And then I'm very excited about that. Sorry, Matt. Losing about half of my advisees this year. It's been a pleasure having Matt as an advisee, and that we've had good times, especially the Yh2RD tutorial this year, and studying Mir together. At any rate, Matt's going to be talking to us about PCBs, and that what he is excited to move on to do is actually work and act. He's tired of school. He wants to do something with his hands. Sciencey, of course. Okay. Without further delay, it's Matt.
Hello, everyone. I'm going to talk to you guys a little bit today about PCBs, specifically destruction techniques and possible methods for recycling them. So, what are PCBs? PCB is short for polychlorinated biphenyl, which means we have 2 phenyl rings with anywhere from 1 to 10 carbon substituents on them. The formula is C12H10-N ClN, where N is just the number of chlorine atoms, and N can range from 1 to 10. This gives us 209 possible congeners, or orientations, or arrangements for these atoms. So not only can they have between 1 and 10, but you can also move the chlorine atom around to different spots on the ring. So this one, for example, here is H5Cl5, because we have 5 chlorine atoms and 5 hydrogen atoms. So in an industrial sense, PCBs were marketed under the name Aurochlor is the most common. There's a few other ones, but this one you hear most often. They were sold as a mixture of congeners, so a whole bunch of different levels of chlorination on these PCBs, and they're numbered 12XX. 12 is the number of carbon atoms, and then the last 2 digits were the percent by weight of chlorine. This Aurochlor was used as additives in a lot of industrial purposes, paints, rubbers, carbonless copy paper, industrial electronics like transformers and generators. And the reason it was used in those is because of a few factors. It has a high flash point, so it takes a lot of heat for these things to combust. That makes them very flame resistant. So they'd add it to rubbers, add it to paints, and this would make them much more resilient. It also has a low electrical conductivity, which means it's useful as an insulator. In addition to its flame-resistant traits, makes it great as an insulator in electrical applications. A few other traits of PCBs is that they have low water solubility, and they are lipophilic, which means that they are attracted to and accumulate in fat cells. So there's also a general trend that the more chlorinated PCBs are more lipophilic, and that can even be extended to more chlorinated PCBs are generally more toxic and more dangerous. Because of this lipophilic nature, PCBs are known to bioaccumulate and biomagnify. So what that means is that as they get brought into the food chain through plants, through small animals, insects, fish, the PCBs accumulate in the fat tissues, and then as the energy moves up the food chain, as the small animals are consumed by the larger ones, those PCBs stay in the bodies and continue to accumulate in a mass in the larger animals. The PCBs are known carcinogens, and they specifically target the liver and the endocrine system, and have other minor effects on other parts of the body. They're also, because of the other traits, they're low solubility, their low or their high resistances, they're very resilient. So the reason that these were created was because of their resistance, and this is also the reason that they're creating so many problems for us, is because they're so resistant and they stick around the environment and refuse to break down. Because these things are so bad, they were involved in the Toxic Substances Control Act, 1976, and PCBs were specifically mentioned as being banned from manufacture, processing, distribution, or use. A few things to point out about the wording of this. One of the big ones is they can't be used except in a totally enclosed manner, which in an ideal world, okay, sure, you can have a totally enclosed manner, a perfectly enclosed manner, but that isn't always the case. You know, accidents happen. You know, what happens if your transformer gets struck by lightning and then your PCBs leak all over, right? And then you have a problem. In addition to this, it doesn't limit the ones that are already in use. This is continued or future use. There's actually a few stories I found. When this law was passed, they put a lot of regulations on proper disposal of the PCBs. And so there's stories of these chemical companies that were sitting on all this R-chlor and didn't want to pay to have it properly taken care of. So they would load it up in the truck and forget that one of the valves was open and drive down the road and just pour it down the road and in the ditch, and oops. So to sort of bring the PCBs a little closer to home, they were used in the production of carbonless copy paper. And as you all know, there's a lot of paper factories in Appleton and up and down the Fox River. And through the manufacturing process of this carbonless copy paper, a lot of PCBs ended up in the river. Due to their low water solubility, a lot of them ended up in the soil of the riverbed. And there's currently cleanup operations underway in an attempt to remove these PCBs from the riverbed. So what they do is they have these barges with dredges on them, and they literally pull the soil up from the riverbed and take this contaminated soil and pull it out from the bottom of the river. And then they cap it. They lay down fresh sand and gravel, and depending on the concentration of PCBs, this example here is 10 to 50 parts per million in the soil, dictates how thick of a cap they put on. This one here, the gravel and sand is 16 inches. They have anything below 10 parts per million, they do just a 6-inch sand layer. And then anything above 50 parts per million, they actually basically double that 16 inches up to 33, and most of that is just more gravel. And basically just try and cap whatever PCBs are remaining and keep them at the bottom of the riverbed. So now we pulled all this contaminated soil out of the bottom of the river, so what do we do with it? A lot of it ends up just being trucked off to landfills, where it's just thrown back in the ground. And we've kind of solved our problem. We got it out of the river, but then we just threw it back in the ground again and haven't really done anything to treat these PCBs and improve this soil. The more contaminated soils are sent off to special waste treatment facilities, where they basically just throw them in an incinerator, which tends to create a lot of nasty compounds in itself when these PCBs are violently ripped apart. So the papers I looked at for this presentation involve different methods for the destruction and decomposition of these PCBs. First one is heat. I already mentioned the incinerators, but there's also superheated water. We have sonication, which is ultrasonic pulses, and then we have radiolytic degradation, which is the use of gamma rays. And so what we're looking at when we're trying to destroy these PCBs is we're looking to remove the chlorine atoms from the rings. Ideally, we want to remove all of them, but that gets, as you get fewer and fewer chlorine atoms on there, that gets increasingly difficult. But if you remember, there's the general trend that the more chlorines it has, the more toxic it is. So if we can knock a bunch of them off, then we have improved our status where we were. We also want to look at the efficiency of the techniques. Are they thorough? Sure, we can pull all these chlorines off, but are we getting every single one of these fully chlorinated PCBs? Safe conditions. We don't want to have to expose workers to crazy conditions in order to get this done, or expose them to the dangers of the PCBs themselves. And the last one is inexpensive. Unfortunately, a lot of these things are governed by how much it's going to actually cost to do this. So the first one is subcritical water dechlorination of PCBs with metal additives and in waste paint. So for this this research, what they did is they just went to the hardware store and bought some steel tubes and caps, put some water in them, and then either used a standard of a PCB standard, or they used paint chips that were known to have PCBs in them, and they put them in an oven and cranked up the heat. Because they were in these sealed steel containers, they were able to withstand the immense pressure that was created from the heating, and that kept the water from boiling, but still allowed it to get really hot. And so the temperature that they used most was 350 degrees Celsius, and as you can see down here, that's 170 atmospheres of pressure inside this little tube once you get it up to temperature. So what they found is that when they heated up the standard, the plain PCB sample, they didn't get much degradation. They got a little bit. Here across the x-axis is how chlorinated the species are, and the y-axis is the amount of PCBs recovered for each one. The white bars are the initial composition, and the black is after 1 hour at 350 Celsius. So as you can see here, this is the standard. There's a little bit of destruction of these, but not much. Another thing you want to look at is, in addition to the lowering of the peaks, you want to look at the general trend. Just because these peaks came down, we knocked a few chlorines off all of them, but we didn't knock a lot of chlorines off the really chlorinated ones. So we still have highly chlorinated PCBs and still have dangerous material. In the paint samples, they found that not only did these concentrations get knocked down a lot, but there's also a shift from being centered around the 5 chlorine molecule to now to the 4 chlorine molecule. So not only did they knock a lot of chlorines off, they also knocked a lot of chlorines off the highly chlorinated ones. So there's a lot of variables that they tested in this sample. They did a lot of repetition too. All the samples were repeated in triplicate. There's lots of standards done, lots of testing to make sure that the temperatures were exactly where they wanted them to be. And so things that you can vary is the temperature that they're heated to. The general trend was that higher temperatures increased the decomposition and shifted the peaks more to the less chlorinated ones. You can also increase your heating time. So they did from half an hour to an hour to 3 hours of heating time. And the more that you heated it, the more decomposition you had, although there was diminishing returns. Once you hit a certain point, the amount of destruction kind of falls off. They also looked at the metal additives from the paint. They determined that there was mostly lead, copper, and aluminum in this paint, and they spiked some samples with lead, copper, and aluminum to see which ones would have a greater effect, and they found that lead had the greatest effect, then copper, then aluminum, in assisting this decomposition. This graph here shows how the increased temperature affects it. So our white bars again are our initial concentration, and then the gray ones is 300 Celsius. So we can see a little bit of a shift. These are definitely lower than the initial peaks, and we're shifted down to the lower end here. And then the dark one is 350 degrees Celsius. So we cranked up another 50 degrees, and you can see that we've really shoved this graph as far to the end as we can. So there's continued dechlorination of the PCBs. The next method is gamma ray destruction. So we have gamma ray destruction of PCBs in isooctane and transformer oil. So this one, they took an old transformer that uses PCBs in its insulating fluid and dunked them in a pool. This is spent nuclear fuel storage, and they put the spent nuclear fuel at the bottom of this pool to insulate against the radiation, the gamma rays that are emitted from it. They placed their samples of the transformer oil in little vials, and then they had a tube that is lowered down into the pool, and just to keep the sample from getting wet. So here's a little illustration of that. They use sensors inside the tube and then inside the sample to determine the dosage of radiation that was received. As you can see here in this graph, as our absorbed dose of radiation increases, you can see that the concentration of our PCB here decreases significantly. I looked up some of the doses that they were recording. It's something like thousands of times of what it would take to kill a human. So this is definitely not very safe conditions, but it's mediated by the pool of water. And the final and I think the most promising technique is cavitation chemistry of polychlorinated biphenyls, decomposition mechanics, and rates. So what this means is that they use a sonicator, stuck it in the liquid sample, or the PCB solution, and the ultrasonic waves created by the sonicator create these little bubbles, these little cavitation sites where air is introduced to the solution, and then as these bubbles are created and destroyed and interact with each other, you get very extreme conditions that the PCBs are then subjected to. So it's estimated that you get temperatures of 1700 to 1900 degrees Celsius, which, as we saw before, is crazy hot, and the heat is useful for destroying the PCBs. You also generate radicals, which is a similar process as to the way that the PCBs were destroyed with the gamma rays. So here's a little illustration of one of these bubbles collapsing on itself. They also determined that higher intensity sound created higher temperatures and pressures within the solution. So if they found that something was giving particular trouble, they could crank up the intensity and see if you could get more out of it. So in conclusion, PCBs are pretty nasty. They're dangerous things. They cause cancer and other health problems, not only in plants and animals, but also in humans. And the properties that made them useful, their resistance to heat, their resistance to anything is what's making them such a big problem. They stick around and they refuse to go away. But we're not, we aren't completely doomed by PCBs because there are methods to safely destroy them, including extreme temperatures, extreme pressures, and radioactive conditions. And the sonication seems to be the best solution for decomposition, as it brings them all together and in seemingly the safest manner.
Did they talk about what products are being made from the decomposition? So like, like obviously ripping off the chlorine is great, but where's it going?
Right. So a lot of it is in the most of the solutions were just water or other organic substances. I'm not sure exactly what was made, but it's something with within those solvents. Yeah.
So for the gamma radiation treatment,
Yeah.
the destruction.
Yeah.
So how do you know necessarily that it doesn't go? So it was chlorine 8, I think, is the one that you had shown. How do you know that that doesn't necessarily then go back to chlorine 5?
Oh,
or something? Are they able to measure that as well?
Yeah, it will. That's a generally accepted thing. We saw it in the other graphs as well, where as you remove some of these chlorines, you basically shift from heavily chlorinated to less chlorinated. And so
and that also happens with this.
this will
Thing being ripped apart?
Right. This will happen as well. There's a graph from the paper that was really confusing, where they tried to put like 10 different different PCBs with different chlorination levels and try and put them all in the same graph so you can see it, but it's really messy. And but yeah, they will degrade to the like less chlorinated ones.
I have a question.
Yeah.
So all of these methods are in water, and we talk about the low solubility, and it's really in the soil now.
Mm-hmm.
How do we deal with that transfer? Can we use these methods for the soil, or do we have to mobilize it from the soil into the water in order to destroy it?
That's a good question.
Okay,
I don't know.
Curious.
Actually, in the papers, they never addressed it coming from the soil. I just know that the soil is a local example of how they're relevant. Most of the ones in the like the paint one, for example, they put the paint chips in some kind of alcohol, I think, and basically agitated it for 24 hours to dissolve it into a solvent. So I guess something similar would have to happen, but it would be difficult with dirt. I don't know how you approach it. Yeah.
Why are they so darn stable? Why do you have to like put them in such extreme everythings? Why don't like bacteria chew them up, or sunlight destroys them, or something?
They're stable because they have a very what's what we're looking for. I don't know what we're looking for. There was some mention of some bacteria that could possibly chew them up. Was things that were the process was a little less understood, and there was some stuff I did see about UV radiation, like from the sun, that could also break them apart, but they were in a similar vein as this, using radiation to destroy them.
So in the cavitation process, you say that the temperature approaches 1700 C. Is this also occurring under pressure? This is the heat of vaporization.
Right.
It's being released. So is this also under pressure under that mechanism?
The way it was discussed in the paper, the way I understood it, this is something I hadn't seen before until I started reading this paper. It's something that happens on a very small scale. It's not something that's happening across the whole solution. It's just at these points.
Right, but it's a solution under pressure also.
I don't believe so.
Okay. It's the atmosphere.
I believe it's just happening in the small cavitation zones in the solution.
Temperature would have an odd definition under these circumstances.
Right.
Very localized.
Right, because yeah, yep.
What sort of time scale? Did they talk about how long, like how long it took to get these doses?
Don't quote me on it. I have to double check the paper, but I think it was under an hour. They basically lowered the samples in and waited. Yeah, I think it was under an hour, and then by the time they pulled them out and checked the sensors, they could determine what their dosage was, and they did, obviously, to get the different dosages, they had different samples in for different lengths of time, but I think it was under an hour.
There is, I mean, and then the follow-up question is, so
Yeah.
this was another instance where they just had the PCB in solution, just
Right. This
without
was,
anything else. It was just like they suspended it or they dissolved it in there so they could just get the information.
Right. This graph is that way. Yes. They did test. They tested them in a couple different solvents, as well as the actual transformer oil from a decommissioned transformer, and they all had similar graphs to this one. This one just comes out the cleanest.
The reason why I ask is, I mean, knowing how it interacts when it's in, so you don't have to go through all those extra steps of cleaning it out first.
Right. Right.
If
And
you
then,
just run it through, then you destroy it, and that was the reason for my earlier question. Like, okay, what other products? How do those? You can just shoot the oil straight through it.
Right.
In a coil that gets exposed for an hour.
Right.
You're done.
Right. And then
it's a constant flowing process the manufacturer will look at.
Right.
Versus, oh yeah, we ran the sample great.
Right, and I think that's what the ultimate goal was to make it quick and easy, so that you can literally just drain these old transformers rather than and subject them to the radiation. That was the ideal goal. I don't know exactly how well they determined that, how feasible that was.
In your reading, did you find that there are lots of brominated flame retardants, right?
Yeah.
You know, so if I lick the chair,
Yep.
I've got plenty of them circulating through me and all that. Are they just as tough? I mean, it's a similar structure. There's just a methyl group in between the two benzene rings with lots of bromines.
Right.
Are they just as tough to beat up and tear apart as PCBs are?
I hadn't even considered it until I was talking to Deanna yesterday, and she said, "What if you put something other than chlorine on there?" And I was like, "Whoa!" Like it blew my mind.
Science is soft like a leg.
So I read a little bit about it. There are PCBs that are used as flame retardants. What I understood, they're dangerous like PCBs, but not as bad. In just my brief reading about them.
They'd be more stable or less?
I think that they're
What's strong? Carbon chlorine bond? What's longer?
right. So it should be the bromines are larger atoms that have a longer bond. Right.
Yeah. We can look.
Right.
That brings to my next question. So,
We don't want to go to faculty meetings, so
No,
we're just going to keep asking questions.
So the structure, are there any compounds that are, I assume these aren't naturally occurring?
No, these are entirely man-made.
Okay, so is there anything similar that's naturally occurring that we could look at? Like, well, how did nature do it? It's got to be figured out.
Yeah.
Well, actually, I'll let him answer, and then
I don't have a good answer for that. So
Oh.
Go ahead.
What? Oh, milk. Milk actually adds flame retardant, so they're just trying to figure out how it doesn't get so rancid. Suppose they'll just take milk proteins and chlorinate them and then use that as flame retardant.
Part of nature's transformed.
Makes me feel true.
Other questions?
You're not concerned about the monochlorinated version at all?
In the grand scheme of the PCBs, they're the least of our worries, I guess.
And the most difficult to
Right,
about.
right.
And one more question, because
Yep.
it scared the crap out of me going, oh, these things are gonna eat us all. How prevalent are they? Like, if I went out and just like, well, not in apples, but like somewhere. Pick your Kansas, let's just pick that one.
Yeah.
And I scoop up the soil, how common is it to find these things?
That's a good question. I don't know. I don't think that they're at levels that you would have to be concerned about unless there had been some direct involvement of that area with it. So like what I was talking before, where they just dumped it in the
The trucks driving.
right. So unless a truck drove through there and it's been heavily contaminated, I don't think it's something you have to worry about.
You're not as screwed as with lead.
Good.
Can the mono version?
Oh, sorry.
I just want to know, because I want to bring back to beer. I wonder,
Okay.
can they appear in beer? Because you have chlorophenols in beer. So, can they? I don't know.
I don't know.
Yeah, if phenols in beer,
Yeah.
you're not gonna have vodka. Liquid sometimes look a little bit like
Right. The phenols you're talking about are single benzene rings. This is
Exactly, that's what I meant.
So
that.
It
yeah.
doesn't
The
do
difference
that.
with phenol and phenol.
Right.
Phenol is an enzyme of phenolation.
Gotcha.
It's like phenols.
Gotcha.
I'd be more worried about BPA and canned beer.
Right.
Yeah.
And that's interesting, I mean, that you're worried about lead, because of the first, like, the destruction under the high temperature and pressure.
Right.
Worked better with lead. I was like, okay, are we sure to get ourselves in the foot by using lead?
Right. I don't.
Because copper is not all that better, and aluminum
Right.
is.
Right. And
Which is nickel.
what's that?
Iron and nickel, you nickel difference.
Right. And the aluminum was the one that was the least effective of the three. So it's you kind of have to weigh which one is. If this is something that you're going to be adding to them to destroy them, you have to weigh which ones are most effective versus which ones are most dangerous.
But adding a precipitation process afterwards would probably be more accessible for some of these heavy metals. So if you had to use it in large volume, you just would have to have a good cleanup procedure, which we have. Lead would be better than the PCBs
Well, yeah,
in this
and
situation.
it goes back to the question of, okay, how are you doing it? Are you extracting? Are you extracting it all then destroying them, or are you just destroying them sort of like as they were?
Right. Right.
Yeah. Sort of weird questions.
Other questions? Well, thank you very much.
Will you send me